because we have sines and cosines mixed together with this problem, there's a good chance that we can use identities to get rid of some of those so that we're only dealing with either sines or cosines. And so one idea that we realized in class that would be really helpful for this problem is this minus sine squared piece right here. Let's go ahead and actually add sine squared to both sides. This doesn't always work, but it does work really nicely in this problem. When you add sine squared to the other side, you end up with sine squared plus cosine squared, which hopefully you recall is one of your very basic identities. Sine squared plus cosine squared is equal to just a 1 on that side. And so right away I can get rid of some of those extra pieces, and I'm left with just 3 plus cosine, or 3 plus 2 times the cosine of theta, because I've added that sine squared to the other side. And so just like that, we've gotten rid of our squareds and our mix and match sines and cosines. So let's solve this like we've solved every other problem earlier in the week. First of all, be careful that does not become 5 cosine theta. Think of it as 3 plus 2x. Those are not like terms, so do not combine those. Instead, let's go ahead and subtract that 3. So I end up with negative 2 is equal to 2 times the cosine of theta. And then dividing both sides by 2, I get negative 1 equals cosine of theta. Okay, so looking then in our trig chart underneath the cosine column, I see that there is one angle that gets me a cosine ratio of negative 1, and that angle is just 0. And because it's quadrantal, I don't need to worry about figuring out what quadrants this is positive or negative in. It's a quadrantal angle, so it's the only solution I get. Oops, I'm sorry, it's not equal to 0. What am I doing? I'm sorry, the one angle under the cosine column, I was looking under sine or something, I think, is pi. So again, though, it is the only solution. There is only one angle that gets you a cosine ratio of negative 1, and that's pi.